Here we are, Chapter 5, Section 5.4, Orbital Diagrams and Electron Configurations. After this video, go and check out video problems 16 through 18. What we're going to do this time is I'm going to skip down to electron configurations, go over electron configuration with you, and then come back to orbital diagrams. Now, this is a very important section to know and understand and to be able to do, and to be able to think about quickly. So make sure that this is a section that you have down pat. All right, as we get deeper and deeper here into the subject, certain things are really, really important, while other things are just very important. So, all right, let's skip on down here to number 2, electron configurations, right? Because then after electron configurations, we'll jump back up to orbital diagrams. So, electron configurations, these indicate the placement and energy of electrons in an atom. Now, up until this point, we have what's called the Bohr model. And the Bohr model, I mentioned it before, so here's the nucleus. In the Bohr model, they thought these electrons lived on orbits, which an orbit is a defined distance from the nucleus and also a defined energy from the nucleus. Well, there was a problem with that called the Heisenberg uncertainty principle, which simply stated that you can't know the momentum and the placement of an electron at the same time. Well, the problem with the Bohr model then is we know exactly where it is. And according to Heisenberg, that can't happen. So we come up with the wave view of the atom. The Schrodinger wave model is what it is. That we'll get into more in AP. But for now, a couple things that you want to know. With electron configurations, you go from lowest energy to highest energy. So that's how we always do our electron configuration, from lowest energy to highest energy. And then we also indicate the number of electrons as a superscript. And you can find all sorts of examples of this as you go throughout. Let's go to a periodic table real quick. So I just happen to have one over here. So here's this periodic table. All right, and a couple things that you need to know for electron configuration. All right, so first, groups 1 and 2. Groups 1 and 2, and that includes helium. Those are what are called the S block. So that's the S block. Okay, now groups 13 through 18. These are what are called the P block. All right. Groups 3 through 12. Right here. Now this has a special name. These are what are called the period -1 D block. Okay. And then finally down here we have the F block, that beautiful burnt orange color. So that is the F block, and it is the 4F and 5F. All right. Now, just to let you know, the F block actually belongs right here, and you can tell because it goes from 57 to 58. Okay. Then it goes from 89 to 90. Now, these are actually called the actinides and the lanthanides, but all right. So keep this in mind. S block, groups 1 and 2. P block, groups 13 through 18, period -1 D block, and then finally the F block. All right, so let's do this. Let's try the electron configuration of a couple of these, and I think you'll catch on quickly. All right, so let's talk about hydrogen. So what we want to do is we want to describe the energy and sublevels of these electrons. Well, hydrogen has 1 electron. Remember, it's got an atomic number of 1. That means it has 1 proton, which means that it has 1 electron. So the electron configuration of hydrogen, let's see, where is that electron? Well, it's on the first period, which is the first energy level. So it's on the first energy level. It's in the S block, so we call it S. And then it only has 1 there, so 1s1. Okay, let's do helium. So helium's over here. It now has 2 electrons. Okay. And those electrons are both in the first period, first energy level. They're both in the S block, but now we have 2 of them. Let's skip down and do lithium. So here's lithium. Okay, so lithium, it's in red, that's okay. Okay, now it has 3 electrons, and electrons, they fill the lowest energy level first, and then they move up. Okay, so the first 2 electrons are going to go into the first energy level. They're going to go into the S block, and then I'm going to put 2 of them in there. Now, think back to, I'm going to skip back here to the notes real quick, and let's remember back to right here. What is this? Section 5.3. We said the S shape has 1 orbital which can hold 2 electrons. So let's go back to our electron configuration. Look, here's the S shape. How many electrons can it hold? It can only hold 2. So that's what we call full. So that's a full S sublevel. So since that's full, I need to go to the next level, which is the second energy level. So I put a 2. It's still in the S block, and now we have 1. So altogether, we have 3 electrons, and that's how many electrons lithium has. All right, let's skip over and let's do carbon. So here's carbon, has 6 electrons. Okay, so again, the first 2 electrons fill the first energy level, and those are both in the S. So we go through the first period. So there's the first period, and so there's 2 of them in there. Then we go to the second period. The first block that we run into in the second period is the S block, and there are 1, 2 electrons in there, and that's full. Remember, S can only take 2. And then we skip all the way over here. It's still the second period. This is, where'd you go? This is the P block, and there are 1, 2 electrons in the P block. Okay, let me show you something real quick. So we're going to go back to the notes. Going to go back to that section that we were just looking at. Yeah, that's fine. We can do that. So let me grab this real quick, and I'll right there. Go back to that periodic table. Let me just paste this up here, maybe. All right, it's in the way. Over here. Okay, so let's put it right there. Okay, we said S has 1 orbital, can take 2 electrons. Check it out. Am I going to do this in? Let's do this in purple. So 1, 2 electrons. We said P has 3 orbitals, and it can take 6 electrons. 1, 2, 3, 4, 5, 6. And then it's full. We said D has 5 orbitals. It can take 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And finally, F has 7 orbitals. It can take 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the periodic table is set up in these sublevels. I usually teach this just with the periodic table. There's other ways to teach it, and you can find them. You can seek them out yourselves if this doesn't work for you. But generally what I found is that most students do okay by just using the periodic table, and you will always have a periodic table given to you. Always. Okay, let's go to sodium. So here's sodium. Okay, now, to get to sodium, we're going to have to go through the first energy level. So we're going to have to go through this first energy level. We're going to have to go all the way through the second energy level, and then we're going to end up on the third energy level. So let's go ahead and try this out. Sodium. So we go through the first energy level. That's 1s2. Now that's full, right? So we go to the second energy level. That is 2s2. Not full yet, so we got to go over to the p's. 2p6. So now it's full. It can only take 6 in the P, so that leaves me with 3s1, and there's only 1 in that 3s sublevel. Alright? Okay, let's skip down and let's do vanadium. So here's vanadium, right down here. Okay, it's further down. This may be the last one we have to do. We'll do vanadium, and then we'll do selenium. This one right here, okay? And then I'll show you the shortcut. So first let's do vanadium. So here's vanadium. Now, to get to vanadium, I have to go through the first period. I have to go through the second period. I have to go through the third period. I have to go through the 4s, and then I end up with these. All right. So let's go ahead and do that. Here's the first period, 1s2. Here's the second period, 2s2. Here's the third period, 3s2. Oh, wait, made a mistake. 2s2, we got to go to 2p6. 2p6, Hopefully you got that. 3s2. Now I got to go all the way over here to 3p6. That's full. So now I'm right here. So it's going to be 4s2, 1, 2, 3. So I got 3 in the D block. Notice it's called period minus 1. So this is the fourth period. So 4 minus 1 is 3, and it's D3. Okay? So looking at that, it's all the way through the 4s and then the 3d3. Okay, so that's why it's the period minus 1. You subtract 1 from the period. So let's do selenium, and then we'll move on. And you can check out some of the video problems for some more help. So selenium, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, because there are 10 of those elements to get all the way through the D, and then we go back to 4p4 in this case. All right. Now, there's something special about a full orbital. A full orbital is incredibly stable. So what is a full orbital? A full orbital is an s2p6 configuration. So look at argon. So here's argon, right? So let's talk about argon. Argon has the electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. So that's full. We can't put any more into that third energy level at this point. This is such a stable configuration. We refer to it a lot, and we can actually use that configuration, that S2P6 configuration, the noble gas configuration. We can use that for a shortcut. So let me show you the shortcut. Let me move something here real quick. Move. Okay. So check this out. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. So look right here. Oh, grab a pen. Right here, look. There it is, right? So what I can do for vanadium here is I can put argon in brackets and then write 4s2, 3d3. And that's called the noble gas shortcut, or the abbreviated configuration, shorthand notation. Now, this is very important. You always use the noble gas that comes before the element. So let's do selenium here. So here's selenium. What's the noble gas before the element? Argon. So this one's going to be argon as well. So selenium becomes argon in brackets. Did my bracket too big? 4s2, 3d10, 4p4. So remember the rule. It is the noble gas before the element. Okay, so look at something like sodium. So sodium's right over here. Right? What's the noble gas before it? The noble gas before sodium is neon. Right? So this 1s2, 2s2, 2p6, that becomes neon 3s1. Okay? So again, electron configuration, very important. Practice it as much as you can. Let's go back to the notes. Okay, so let's see. I gave you a bunch of examples. Here's a bunch of examples as well. So here's the electron configuration. Here's the abbreviated electron configuration, also called the noble gas configuration. All right. So now let's skip back and let's talk about orbital diagrams. So I think orbital diagrams are easier once you do the electron configuration. All right. So let me show you how these work. Let's pick one of these to do here. Let's pick carbon. All right, carbon's a good one to do. So let me grab carbon. Boop. And I'm going to copy that, and I'm just going to bring it down here. Okay, so let's call this orbital notation. Let's paste that carbon. Okay. So this is what orbital, with an L, notation is. Basically, it's another way of symbolizing things. We're going to show all these electrons and all these orbitals. Okay, you get a little more information out of orbital notation. So first, it's going to be the first two electrons. Okay, we draw a line like that. Now your textbook shows boxes. It's usually just a line. That line represents the 1s orbital. Now remember, you can go up here. There's only one s orbital. Okay, so that's the first orbital that we have there. And we have two electrons. Now the first electron is pointing up, so it's shown as a half arrow there, and it's pointing up. That's the first electron. Here's the second electron pointing down. Now, the reason why we use an arrow pointing up and an arrow pointing down is because these electrons have a magnetic quality. Okay, they have a spin like they're spinning, and so when they spin, they act like a magnet. All right, and we'll see how that works later on here. But you can't have a north spinning magnet and a north spinning magnet occupying the same area, which is why we have to have one magnet spinning up, one north magnet, one spinning down, one south magnet. Again, they act like magnets. They're not magnets, they act like magnets. All right? So that's 1s. Let's go to the 2s. So again, so now I'm describing these electrons. There's only one 2s orbital, so I only draw one line. I draw an arrow pointing up and an arrow pointing down. So that's 1s2, 2s2. Now I go to the 2p. There are 3 2p orbitals. So there's, I got to draw 3 lines. 1, 2, 3. Right? So those, and I put a little bracket like that, those are the 2p orbitals. Right? Now, there's something called Hund's rule. And Hund's rule basically says orbitals of equal energy will each get one electron before any gets a second electron. Now, all of these 2p's, it's a px, a py, and pz, all of these 2p's have the same amount of energy. So what that means is, there are 2 electrons here, what that means is the first electron will go here, and then the second electron will go into a different orbital. Now, I often say this is like the summer camp rule, maybe the dinner table rule, and that is everybody gets one before anybody gets a second. So you know you can't have seconds on something at the dinner table before everybody else has their first. Right? Everybody has to get some, and then you can go back in for seconds. Well, same thing here with electrons. The orbitals of equal energy each get one before they get a second one. Right? So let's look at another one here. Let's do one that we haven't done yet. Let's do oxygen, and that's a pretty good example too. All right? So here's oxygen. Why don't you pause it right now and do the electron configuration of oxygen. Go ahead, pause it. I believe it's that, 1s2, 2s2, 2p4. I should probably get a periodic table out here in front of me. Periodic table, 1s2, 2s2, 2p4 is correct. Right? So let's do the orbital notation of oxygen. Right? So it's the 1s, there's only one s orbital, 2 electrons there. 2s, there are 2 electrons there. And now we go to 2p, there are 1, 2, 3 p orbitals. And then we have 4 of them, so it goes 1, 2, 3, 4. Everybody got 1. Then I came back around and gave a second electron. And here you can see how it's full. All right? Each one of these orbitals can only hold 2 electrons. 2 arrows, 2 electrons. So you can see that it's full. All right, let's try one more. I'm going to have you pause and predict here. Let's do vanadium. Okay, but we're going to use the noble gas shortcut for vanadium. So it's going to be, what is it? We did this one. You know what? Let's not do that since we did it. Let's not do chromium. Let's do 1, 2, 3. Let's do manganese. No, let's not do manganese. Let's do iron. Let's do iron. Sorry. A little bit of confusion there. So we're going to do iron. It still has argon as the noble gas before it. So here's iron. Here's the noble gas before it. So it's going to be, what is it going to be? It's going to be posit. 4s2 3d3 3d6. Yep, 3d6. All right. So let's do the orbital notation. Tell you what, why don't you pause it? We're only going to do the orbital notation of these. Why don't you pause it, go ahead and do the orbital notation, and then let her run, and I'll show you the answer. So D has 5 different orbitals. 1, 2, 3, 4, 5. Everybody has 1. I go back, give a second right there. Now, remember I said that these electrons have spin-like quality, and that makes them sort of act like a magnet. Iron, of course, is attracted to a magnet. Why? Because there are these 1, 2, 3, 4 unpaired electrons in iron that have this magnetic quality. And so anytime we see an electron like this that is not paired in an orbital, it's what's called paramagnetic. It's attracted to a magnetic field. Okay? All right, so let's just double check all the notes here that we have for section 5.4. Make sure we covered everything. Yeah, looks good. You know, you got your S, P, D, and F. Remember, you know, these are all in the same energy level, right? F has the highest, S has the lowest, and we always draw our electron configuration and orbital notation from least amount of energy to most amount of energy. All right. See you in a little bit.